This meeting is being recorded.
Hello, good morning, good evening, good afternoon, everybody, wherever it might be. It is my great pleasure to welcome Ralf MEYER from Göttingen, who will tell us everything and more about correspondences between graph sister algebras. Ralf, the Zoom is yours, the floor is yours. Take it away.
Thanks, Piotr, for this invitation to speak again in this seminar. Today I will be talking about my most recent article, which is joined with Rasmus Bentmann. And the goal of our project was, well, to classify graph C-star algebras in the non-simple case. We didn't reach that goal, but we made some progress about it. So the question in the subject would be, are graph C-star algebras classified? By, let's say, just a K-theoretic invariant. And here, of course, the important thing is even if they are not simple. Many of you will know that a simple graph C-star algebra is either purely infinite or an AF algebra. And in both cases, we know very good classification results. And in particular, K-theory is a complete invariant for these things. But graph C-star algebras don't have to be simple. And if they are not, then the ideal structure can be pretty complicated. So therefore, this is really a difficult question. One particularly strong result, if you don't impose any further restrictions, would be work of many people, including certainly Søren Eilers and Efren Ruiz and a couple of more people. They were able to complete the classification when you have a graph with only finitely many vertices.
Which means unital sister algebra.
Yes. But this unital might be slightly misleading because having only finitely many vertices actually is maybe also imposing other conditions, like for instance, the ideal structure is also forced to be finite if you have that. Graph C-star algebras are usually not unital. And there's really a large realm, and it's really also much more general. So many things that can't happen in the unital case could happen in general graph C-star algebras. So this was solved before we even started, and that's kind of a well-known and important result. What was also solved was purely infinite graph C-star algebras with only finitely many ideals. And in these cases, the classification was also finished by Rasmus Bentmann and myself in earlier papers. So we found some invariants of a K-theoretic nature that would do this classification. And well, in the end, the only thing that our newest preprint could achieve was to get rid of this restriction on the ideal structure. which is an important deal because if your ideal lattice is not finite, it could be pretty complicated, and so the usual invariants people have been using before don't work so well if you go beyond that case. Also, the techniques we had developed using homological algebra in triangular categories, they don't generalize to this situation in any obvious way. So you needed new ideas to actually get started working with C-star algebras with infinitely many ideals. Well, using a new approach, which is also very graph C-star algebra specific, maybe unfortunately. So my previous work with Rasmus was mainly about purely infinite C-star algebras in general. So there is something special about graph C-star algebras in these results sometimes, but many of the techniques would work in the same way for arbitrary purely infinite C-star algebras, and there was only a few places where graph C-star algebras are any special. And so the new idea is actually also more elementary. So the approach is new and in some sense easier, more elementary than the previous techniques. In the very end, to get this new result about the purely infinite case, we have to go back into the Kirchberg classification theorem for purely infinite non-simple C-star algebras.
Sorry, could you remind me, this purely infinite, it means what?
Purely infinite, what we actually, well, in the graph C-star algebra case, probably all definitions are equivalent. What I really mean here is O infinity stable. So O infinity tensor A is isomorphic to A. Actually, once you go beyond simple C-star algebras, there are slightly different concepts of what infinity might mean. And you need a stronger version, which is known to be equivalent to being O infinity stable. And this is what you should expect if you want to have a general classification theorem for non-simple C-star algebras. The invariants that you want to use don't distinguish between O infinity and the complex numbers. And so if these two things are not isomorphic, then you don't have any hope of doing any classification results. This is a bit like Z stability in the simple case. If you're not Z stable, then you have no hope to classify these things unless you use invariants that are fine enough to distinguish Z tensor A from A. And then you get into much more complicated invariants. And actually, this concept of being strongly purely infinite is somewhat technical. I remember, I think that in the case that we could treat earlier with kind of general homological algebra in Keiki theory techniques had the restriction of finitely many ideals. And I think if you assume that, you might be in a case where this strong concept and the usual concept of pure infinite would be the same. But that's no longer true. Well, it might also be true for general graph C-star algebras, I guess, but I'm not certain about this. Let's not claim anything about that.
Okay, so Tomek has a question, and before he asks his question, could you please also tell me this concept of pure infinity not for graph C-star algebra? I remember it's something to do with projections, but I don't remember exactly what.
Actually, if you go beyond simple C-star algebras, and in general, you might not even have any projections. So it's really about the Kunz semigroup. And in this Kunz semigroup, you want to have that even if you pass to some hereditary subalgebra and some quotients, maybe that you have elements which satisfy something like 2x is below x in this Kunz pre-order. So this is kind of the paradoxical behavior that you have in things like O2, O infinity, that there are these non-trivial isometries which would make the unit element equivalent to a halving projection. And you want that this happen, that every element has this paradoxical behavior.
Okay. Tomek? You are muted.
My question is about determining if this condition of strong infinite type can be detected looking at the graph, at least in some cases.
I think that graph C-star algebras should, well, you mean in, of course, graph C-star algebras don't have to be purely infinite. They can be stably finite, AF algebras even. And there are certainly papers that talk about when a graph C-star algebra is purely infinite in the usual sense. And the condition there would probably be something like you have to rule out these components which are like circles, where you have just one loop when you get function of the circle as a subquotient, or that tensor compact that you don't want. Also, the AF case must be ruled out. And I would believe that if there is no subquotient, which is like that, then it would be purely infinite.
Okay,
and
thank you.
At least if the ideal structure is finite, then that would be the same as being strongly purely infinite. And since a graph C-star algebra is an inductive limit of graph sub C-star algebras with, well, which are at least Morita equivalent to something with only finitely many vertices, I think you might be okay with general graph C-star algebras. But better don't quote me about these things. I'm not the greatest expert on this. So in most of my works, I just work with O infinity absorbing, which is meaning O infinity tensor A is isomorphic to A. That's the property that you need to feed into Kirchberg's deep results. And that's the kind of black box which tells you that you can lift a KKG equivalence to an actual isomorphism. And maybe let's also mention a different kind of result, which we also prove along the way. Namely, when I say classified, probably you mean up to isomorphism. And another new result is that we got a classification up to homotopy equivalence, even ideal preserving. So I suppose you all know what homotopy equivalence means. And ideal preserving means that you first choose some isomorphism between the ideal lattice, and then you think of your C-star algebra as being a kind of diagram where you have all these ideals with their inclusions together, and then you want that your homotopy equivalence actually restricts to these ideals so that you get an isomorphism of these diagrams. This is important because in the non-simple case, when you need ideals, you actually want to have an isomorphism in the appropriate ideal preserving KK theory. That's what you can feed into Kirchberg's result. And so that's what also is produced by our theory. So this homotopy equivalence result is kind of elementary. There are some results which are actually deep, you need to know, but if you know kind of the non-stable K theory of graph C-star algebras well, then that's all you really need to understand how to get to this ideal preserving homotopy equivalence, at least in the purely infinite case, which is the one where we can go further. And then you can feed this into Kirchberg's machinery and get a classification up to isomorphism, merely because Kirchberg's deep results would say if you have strongly purely infinite C-star algebras with the same ideal structure, and then if they are equivalent in KK theory, in the appropriate one, ideal preserving one, then they would be isomorphic. And this homotopy equivalence is stronger than this KK theory equivalence, which is ideal preserving. Okay.
So can the lattice of ideals here be replaced by a diagram of graph C-star algebras?
Well, in the end, if you take an ideal in a graph C-star algebra, it's again a graph C-star algebra. So you would have a diagram of graph C-star algebras if you do this. of course, if you have a general diagram of graph C-star algebras, then they don't have to be simple or anything. And so, or if you talk about ideals, of course, there are these subquotients. And at least if you have an infinite ideal lattice, then you don't know whether any subquotients are simple. So I think the only diagrams you really want to talk about would be take all the ideals in a given graph C-star algebra and turn this into a diagram.
Okay, thank you.
That's where this Kirchberg theory is applicable. And this homotopy equivalence is a result for a single graph and getting, well, maps back and forth, which then, when you compose, are homotopic to identity maps. And all these things are such that you know what happens on the ideals. And, well, the fact about ideals is really an afterthought because the K-theoretic invariant that we are going to use determine the ideal structure. And therefore, since all the maps we want to build are, well, first given on K-theory, then lifted to some kind of star homomorphisms, they are by construction, you know what they do on K-theory diagrams, so you know what they do on ideals. And you can arrange and preserve ideals if you have an isomorphism on the appropriate invariant. Okay, I suppose I can continue and talk about how we approach this question. So the idea is that graph C-star algebras are so nice that you can actually describe star homomorphisms out of graph C-star algebras into a stable C-star algebra quite nicely. So we describe, or you might even say classify, star homomorphisms from A into, well, let's say something tensor K. Oh, this doesn't work. So let's say B tensor compact operators, where A is a graph C-star algebra. And another point which I like, instead of these star homomorphisms into a stabilization, you can actually replace these by what I call proper correspondences, A-B correspondences. This is actually a nice point of view because it, well, clarifies some things, I believe at least. So what is an A-B correspondence? This would mean that you have a Hilbert B module. So these are Hilbert B modules with a non-degenerate star homomorphism. Maybe call this thing E, and you have homomorphism from A into the compact operators on E. So that's what I mean by a proper A-B correspondence. And how can you link these two things? Let's say you have a star homomorphism from A into this stabilization. It might be degenerate. In my correspondences, I want a non-degenerate star homomorphism. So what you would do if it is degenerate is you take, well, phi of A, the image, and then you just multiply with B tensor L2 of n. So when I say compact, I mean probably compacts on L2n. And phi of A acts on this, and this is a submodule of B tensor L2n, which is a Hilbert B submodule. And the compact operators on this are, well, an appropriate hereditary subalgebra in B tensor K. So if this is my E, the compacts on E would be the same as phi of A times B tensor compacts times phi of A. And of course here A is mapping into this by phi, and this is non-degenerate as it should be. So this is how you get a proper correspondence from a star homomorphism into a stabilization. To go back, you would need Kasparov's stabilization theorem. Well, maybe for this you need that A is sigma unital, so that the compact operators are then countably generated. So this actually really works if A is sigma unital, but well, so this is a mild assumption, I guess. So by Kasparov stabilization, you can arrange that E plus B tensor L to N is isomorphic to B tensor L to N. And so you can turn the map into the compacts on E into a map on the compacts on B tensor L to N, which we know are B tensor K. And then these two processes are really inverse to each other up to isomorphism. Okay, and when I say classify these star homomorphisms or these proper correspondences, I mean by some kind of K-theoretic data. And it's really a classification up to isomorphism. So we can completely describe these proper correspondences or these star homomorphisms using K-theory data. And I suppose this is where I should start. So what is actually such a star homomorphism? For this, we have to recall what a graph C-star algebra is. And I suppose you all know roughly how it goes. Since there are two conventions, there's maybe some source for confusion, but I suppose the one I would use will become clear from my writings. So a graph C-star algebra is generated by projections PV for vertices and partial isometries SE for edges. Now, a first trick, which might be very well known to you already, is that you can combine these partial isometries into a kind of unitary between two projections, or into a Murray von Neumann equivalence between two projections, if you like. So if you take, if V is a regular vertex, then all the SEs for range of E equal to V, they combine to a Murray von Neumann equivalence between the projection for V and then the direct sum of the projections for the source of E, where I'm summing over all edges in the range pre-image of V. So this is also implicitly explaining my conventions for the graph algebra relations, if this bothers you. So SE would be a partial isometry which links P of the source of E to a subprojection of PV. And if I just sum them all up, I should get all of PV. And so that's where I get this Murray von Neumann equivalence. And I call this thing here U of V. So this, I think of this as being, well, a unitary operator between certain Hilbert modules. So, and since these unitaries contain all the SEs for all the edges going into V, and since any edge ends somewhere, at least if my graph is what's called rho finite, so every the range of every edge is a regular vertex. There could be vertices that don't receive any edge, so sources, but that's that doesn't bother me. But there shouldn't be infinitely many edges going into a vertex. Then my theory doesn't work. So assume that my graph is rho finite. Then if I have this map from my graph C-star algebra, I write C star of G for the graph C star algebra of the graph G. If this goes to the compact operators on some Hilbert module E, this is given by the following things. So I first define some Hilbert modules, which are just the images of the vertex projections. So these are Hilbert B modules. And I also have these unitaries UV, which would be a unitary from the direct sum over all these E of source of E. Maybe there are too many E's in my talk. So there's the add little e, and then there's the Hilbert module curly E. So these would be unitaries. And if I know the Hilbert modules E subscript V, I implicitly know what my Hilbert module E has to be, namely E is the direct sum of all these things. And PV must go to the projection onto the submodule EV, the direct summand. And then I know what the UVs must map to, and then since the SEs are just matrix coefficients of those, I know where the SEs are going. So if I know this data, then I get a Hilbert module E with a representation of my graph C-star algebra. There's one more extra condition, namely the identity map on EV has to be compact. This is because PV is going to a compact operator, and then if you translate this statement to what happens on EV, it means that EV has a compact identity operator. This is actually a very serious restriction on a Hilbert module. This turns out to be equivalent to EV being isomorphic to some projection times Bn So if you have a Hilbert module whose identity map is compact, then the Hilbert module must be the image of an idempotent element in a matrix algebra. And this works even if B is not unital. So in particular, if B is not unital, of course, then the unit projection isn't there, but also B as a Hilbert module would not have a compact identity operator, so this all fits together. Okay, and so now we therefore have a nice description of these, star homomorphisms from C star G into the compact on some Hilbert module, and we see that these correspondences from a given graph C star algebra C star G to a given C star algebra B are determined by these projections. Maybe I write QV for these projections. So I get some QVs, projections in some matrix algebra, and I get these unitaries. Now, the first observation is that up to isomorphism, only the isomorphism class of these EVs really matters. And this isomorphism class of the modules translates to the Murray von Neumann equivalence class of the projections. Okay, and this now leads us to the first invariant that would describe a correspondence. So the correspondence E always induces, I should maybe say a proper correspondence, which I assume from now on. So all my correspondences are proper, meaning that the left action is by compacts. And then this will induces a map, which is a homomorphism from the monoid of, well, projections up to Murray von Neumann equivalence. This was not wanted. In my graph C-star algebra, do the same thing of my target, and I just have a notation for this, which I just call P of C star G, and of course P of B. So this P invariant for a C star algebra is just the monoid of projections in matrix algebras up to Murray von Neumann equivalence. And if you have a proper correspondence, you get an induced map. This is how you induce a map on K-theory after all. You first do this, and then afterwards you pass to Grothendieck groups. And this still works if you have non-unital C-star algebras. It's very basic. You just don't notice the lack of a unit element here. And this determines the Murray von Neumann classes of the PVs, because each of the vertex projection is, of course, giving you an element in this monoid for the graph C-star algebra. So here inside you have the class, oops, this was not Q but a P. You have the class of PV. And this would go now to the class of this projection QV. So the isomorphism classes of these EVs are determined by this map on this particular K-theoretic invariant. Okay, so far so good. I don't see any questions so far. Next, you might wonder, given some classes, well, let's call them QV in P of B, when can we find unitaries between these corresponding, well, the direct sum of range of E equal V, and there was the source of E to E of V for all regular vertices. And of course, this would just say this is equivalent to an equality in P of B, namely would need that the sum of all these Q of S of E, where E is in the range pre-image of V, is equal to Q of V. That's the property that you need. Now we need the first fact about non-stable K-theory of graph C-star algebras, which is a theorem, not by us, an old theorem by people doing graph C-star algebras. I don't remember the names right now. Maybe Pardo, maybe someone else was involved in that. So the statement would say that there's a computation of this P of a graph C-star algebra. The first statement would be that there's a surjective map from, well, just the free abelian monoid generated by the vertices. So this NV means function with finite support from the vertex set to natural numbers. And this means that every projection in a matrix algebra of a graph C-star algebra is Murray von Neumann equivalent to a finite sum of vertex projections. And then furthermore, we know also all the relations, and the relations would just come from the regular vertices. And there would be exactly these two maps. So you can send a vertex to itself, or you can send a vertex to this sum of, well, its sources over all edges in the range pre-image. So the unitaries that we have constructed here give you some relations, and these are all relations. So this would be a presentation of this monoid P of a graph C-star algebra. And so the upshot would be that given a bunch of, well, projections in B, you can take these as the values on the vertex projections of your graph if and only if there is a well-defined map from P of the graph C-star algebra to P of B. So homomorphism between these monoids is equivalent to having chosen these vertex projections in such a way that the unitaries UV for regular vertices at least exist. Now to determine, yes?
Thomas, go ahead.
Yes, I have a question. In your presentation, you are talking about monoids.
Yes.
So is the co-equalizer in the category of simply monoids?
I think so, yes. It's a co-equalizer in that category.
Okay. Thank you.
Okay. So at the moment, we have only talked about existence of these unitaries. Of course, to get the correspondence, we have to choose these unitaries. So an actual choice of the correspondence. It was a typo again. Okay, so you would probably guess that, now we get into K1 data. If we look at these choices of these unitaries up to homotopy at least, that's also in the end where we get some results up to homotopy equivalence, because we can actually describe these correspondences up to homotopy of correspondences. If you think of homotopy of correspondences, so this would mean that you have the correspondence into functions from an interval into something. So this would be a correspondence into these continuous functions into B. And well, you probably know that K-theory is homotopy invariant, and this already is true on the level of these P of C-star algebra monoids. So if you have homotopic projections, they are Murray von Neumann equivalent. So actually, if you have homotopic correspondences, they will induce the same map on P of C star G to P of B, meaning that these vertex projections are really staying the same or only changing up to equivalent things. But you're allowed to change the unitaries UV up to homotopy. The classes of these QV stay constant. So only the homotopy class of your unitaries UV is really fixed if you work up to homotopy here. And that's good because we now get into K-theory data. But before we talk about that, I should first talk briefly about ideal structure and also what does this P of A have to do with K-theory.
Tomek, do you have a question again?
Okay. So let's first take the
but
question.
But you are muted for crying out loud. I mean, unmute yourself.
Okay. I have a question about restriction of the correspondence to 0 and 1, to endpoints of this. How do you restrict correspondences?
By tensoring with the evaluation homomorphism, or by functoriality.
But this is on the level of the algebra, this algebra.
Yes. So if you have a correspondence, let's write it down. So you have an A-B correspondence, and you have a star homomorphism, maybe call it phi, not phi, from B to some D, call this here maybe E. Then phi lower star of E would be defined to be E tensor over B with D, where the left action is coming from phi.
Okay, I see.
At least up to isomorphism. And if you take the evaluation maps, this is how you evaluate this homotopy at the endpoints.
And this tensor product is, again, a Hilbert non-degenerate.
Yes, there is this special kind of Hilbert module tensor product, which was introduced by Kasparov. So you can put on this, again, a scalar product and then take the completion in that.
Okay, thank you. Thank you for this explanation.
Okay, so where was I? So I think the next question I wanted to speak about is how is P of the C-star algebra related to K-theory and to ideals. So,
sorry, Ralph, please remind me. So P of A means projections in a C-star algebra or projections in matrices over a C-star algebra?
In matrices. I always take matrices. I never take projections only in A. It's always in matrices. And what I claim is that, at least for nice C-star algebras, this P of A
yes. Mm-hmm.
As, so the ideal lattice, so I of A means the ideals in A.
Mm.
And then the map from, well, I suppose from, you take an ideal and you take the positive part in the K-theory of the ideal, which is a monoid, abelian monoid, of course. So this diagram. So in particular for graph C-star algebras, this would be true. So the information in this monoid P of A is the same as taking the ideal lattice and then for each ideal taking this positive K-theory part. This is nice because this is something that you would see in usual classification theory. And for this to be true, you need a certain weak cancellation property. So if you think about cancellation, this would be the nicest thing that you might want to have. So cancellation would say, if you have, well, classes in P of A, so you have X, Y, Z in P of A, and you know that X plus Z is Murray von Neumann equivalent to Y plus Z, which means the same element in P of A, then you would like to know that X is equivalent to Y. Now, this property is not something you could expect. In particular, if you take a purely infinite C-star algebra, even simple, so if A was simple, purely infinite, then we know that there exists a projection that represents 0 in this K-theory. So the 0, we also know that P of A in that case is already all of K0. Let's also write this one down. So then P of A is just K0 of A, and the 0 element is the class of some projection where Q is a full projection, so it generates the whole C-star algebra A. It's not 0. And of course, if we had now cancellation, then this is impossible because this full projection Q and 0, well, they would satisfy, for instance, that Q plus Q is the same as 0 plus Q. And if you had cancellation, then you would conclude that Q has to be 0. So if you have a simple, purely infinite C-star algebra, you don't have this cancellation property. It just can't happen. And it's a nice thing it can't happen because you have so many projections. It's nice that this doesn't work like this because you want to have this projection that represents 0 and this is a full projection. But there's a weaker property. So weak cancellation. So the above only if X and Y and Z, let's say, generate the same ideal.
Sorry, Ralph, what do you mean by full projection?
Well, if A is simple, it just means non-zero. In general, full projection means that it generates the C-star algebra as an ideal. So here, it's just non-zero.
Mm-hmm.
So the weak cancellation property says that you have cancellation not always, but you do have it if X and Y generate the same ideal and Z belongs to that ideal. And this is a common property. In particular, it holds for these simple purely infinite C-star algebras, for instance, and it also holds for graph C-star algebras.
And how about commutative C-star algebras?
No, they don't have very good properties in terms of their K-theory in the non-stable sense. So if you have a high-dimensional torus even, I don't think that you would expect any such cancellation property. So if you think about vector bundles, they would always give you a full projection on a torus if it's connected space.
Yeah.
And so if you, once you have, well, take a sphere, you know this example of a vector bundle that is stably but not actually trivial.
Yes.
And then you don't have cancellation even in this weaker sense because these are both vector bundles which are full.
Mm-hmm.
So it doesn't work for commutative C-stars, unfortunately, but
Yeah.
it does work for these kind of graph C-star algebra-like things. So the ones we want to classify do have this property. And now we have already hidden here, we see that if you have a class in P of A, it gives an ideal, just the ideal that's generated by X. And then you also get, well, this X, of course, belongs to the ideal it generates. So it also produces something in this P of I, which you could map to K0 plus of I. And the weak cancellation property would, well, it wouldn't quite say that the maps from P of I to K0 plus of I is injective. We again have this problem with the zero element and so on. But if you have two full projections, so they both generate the same ideal, then if there's the same image, there would be the same element already in P of I. Okay, so the upshot is that this monoid P of A is actually determining the ideal structure. Of a graph C-star algebra at least. In general, you would need to know that there exist enough projections so that every ideal is generated by projections. When I say ideal, I probably have to say that there are the gauge equivariant ideals, have to be more precise here. So in general, you get those ideals which are generated by a projection or by a set of projections, maybe. So there would be those ideals. And if you think about a graph C-star algebra, then these ideals are exactly the gauge equivariant ideals. Wait a moment, that's again not quite true. These are the gauge invariant ideals. That are generated by a finite set of vertices. So if your graph C-star algebra were unital, this would be all gauge invariant ideals. In general, you know the ideal structure of, or you know the gauge invariant ideals of graph C-star algebras correspond to hereditary and saturated subsets of the vertex set. And for such a subset, you can ask whether it is the smallest subset that contains a given finite set of vertices. And this is exactly what you get here as this invariant. So this P of A doesn't determine the complete ideal lattice, but it describes some subset of the ideal lattice, which is, well, for a purely infinite graph C-star algebra, it's actually good enough to determine all the ideal lattice, because if you have these things, you could also look at countable unions, let's say, or things like that, and then you would, or just unions of such subsets, and then you would get all gauge invariant ideals in a graph C-star algebra. And so if it is purely infinite, all ideals are known to be gauge invariant, so you get all ideals. So this is one piece of information that's hidden in this P of the C-star algebra monoid. And then I've already indicated how to map P of A to this I P of A by just taking the support of a projection. So this would be the ideal that's generated by this projection. So I call this the support map. So this ideal is called the support of X. And on top of that, there is also this K0 plus of the ideal and the diagram that these groups form. And so if your C-star algebra B, into which you want to now look at the correspondence, if this satisfies weak cancellation, then you can describe a homomorphism of monoids from P of A to P of B in terms of a map between the ideal lattices together with a map on these K0 plus diagrams, which is what you would expect to see in a classification theorem. So the existing results that classify graph C-star algebras would use exactly such kinds of invariants. Okay, now there is the question about these unitaries. So the unitaries
May I have a question?
Yes.
If you
You
could...
can ask why I'm writing this.
Yes, of course. Yeah, but could you come back to the previous page?
Where?
Below. Yes, the last. Yeah. So this vertical arrow from P of A.
Support map P of A to this IP of A. Yes.
You wrote ideal generated by a projection in.
So IPA is a set of, is just the image of that map. So if you have a projection in a matrix algebra, you can look at the ideal it generates. Maybe you do it first in a matrix algebra over A, and then ideals, they are the same as ideals in A.
But how is it related to B?
Yes, this is just a typo. It should be A there. I'm sometimes writing A, sometimes writing B. This should have been an A.
Okay, thank you.
Very good. Okay, so so far I've talked a lot about this map between these, well, P monoids, which is part of my data, but I also need to talk about these unitaries, and this doesn't talk about them at all. Of course, here I'm going to need K1 data. And so I should first talk about what K1 actually is. And once again, there is a nice computation of K1 for general graph C-star algebras. And maybe I try to go back well, maybe I just recycle my computation here and make some decorations to this. So if instead of this P of C star G, I was interested in K0 of C star G, that is, well, then you would of course take Grothendieck groups of everything. And then you can take differences, so you can actually just take the difference of these two maps. So this is just the difference between this map and that map. And the kernel of this map is what is K1 of my graph C-star algebra. That's how you compute K1 of graph C-star algebra. So you take the kernel of this specific map. And so this is now an exact sequence, and then you can continue with zeros if you like, or I like to draw these arrows with decorations. So a K1 class would be an element in Z of this regular vertices, which goes to 0 under this map. And if you are given this map, maybe I give this a name. I call this map here phi. So for phi, we may choose some correspondence that, well, induces phi on the invariant. So we just talked about this. So if you are given the projections QV, which are giving such a homomorphism of monoids, then there exists some unitaries. Given other unitaries, UV, that also, well, wait a moment. I'm jumping too far here. I should not do that right now. So I can choose a correspondence, maybe call it E. That induces a map, well, from K1 of C star of G into K1 of B, like any correspondence does. And it even induces maps between ideals. Maybe I should use a different notation here. So I want to look at the ideal that's generated by some projection, and then I can take phi of that projection, and it generates some ideal in B. And then I have a map in K1 between these ideals inside my graph C-star algebra. Okay. So the question that Rasmus Bentner and I ask is given a map phi from P of A to P of B, where A is now my graph C-star algebra, and this diagram, or maybe such a diagram is better than this. So by such I mean that I have maps between K1s of ideals, specific ideals in A and B. Such a diagram of K1 maps. Is there another C-star correspondence that induces both simultaneously? So this is an important question. So you believe that this P of a graph C-star algebra and the diagram of K1 groups for all these gauge invariant ideals should be your complete invariant. Maybe you hope that. That's not true, actually. But to understand why it's not true, you should try to prove that it is and then fail and see why you fail and then improve your result. So what you would like to do is you take a map between this P monoid and another map between the K1 group diagrams, and then you want to realize this map by a C-star correspondence. If you could do that, you might then, in the next step, you can go back and forth between two graph C-star algebras and would get correspondences in both directions. And then maybe you can also argue why the compositions induce identity maps on all these invariants, and this is actually good enough to imply that they are homotopic, at least, to identity maps. So this is how our proof in the end will go. So we take our graph C-star algebras A and B, and we assume that we have such an isomorphism between the invariants consisting of these monoids of projections up to Murray von Neumann equivalence, and then the diagram of K1 groups for all the gauge invariant ideals. Let's also write this down to explain why this question is relevant. So So you have isomorphisms between these monoids for two graph C-star algebras and also between the K1s of all ideals. This is phi 1, this is phi 0. And then, of course, we also have get also phi 0 inverse, phi 1 inverse, and assume we could lift these two correspondences E and maybe F going back and forth. So E would be an A-B correspondence, and F would be the BA correspondence that goes back. So you want phi 0 inverse and phi 1 inverse. If you could do that, you could also compose these correspondences, which would mean that you take E tensor over B with F, and F tensor over A with E. And these now, they lift the identity on P of A and on K1 of all ideals. Or on B similarly. And if you know that, first of all, you know that this correspondence maps each vertex projection to an equivalent projection. And by just changing up the isomorphism, you could arrange that it maps it to the same projection. And then you also know that these generating unitaries go to things which have the same K1 class. Now, the relevant corners, so vertex projection times a graph C-star algebra like this, they are known to be K1 bijective. What this means is that the K1 group is just unitaries in that C-star algebra up to homotopy. So K1 of, maybe I call this thing C for corner. This is just unitaries in C up to homotopy. This is a property that's also known for purely infinite simple C-star algebras, for instance. So it's not uncommon to have this feature. And it is also a property of graph C-star algebras. This is something we show in our paper, although we just mainly use the simple case and then use some results of other people about how this property of being K1 bijective can be pushed through an extension to get the general case. So therefore, we know that this E tensor BF kind of maps the generators PV again to PV and UV to homotopic unitaries. You don't quite get that, but you almost get that. There's an extra step that you need to do, which I think for time reasons I might not get to in the end. But it might sound at least plausible that you might get something like this, and what you actually get can be improved a bit more to get exactly this. So at the moment I was acting under an assumption which is maybe not true. So if I could always lift these maps on the invariant to correspondences, then I could go back and forth, and the maps that I get from A to itself by going between A and B and back, well, I have no reason to believe that it is actually the identity map on A, but I have good reason to believe it is homotopic to the identity map, and I can in fact arrange for that to happen if I'm a bit more careful in the construction. So, but there is an issue, namely, I wanted to say that I can lift both maps simultaneously. I need both maps simultaneously because I want to argue that both the PVs and the UVs go to the same thing. And that is more difficult because at the moment I have only said that I can realize this map phi 0, here, this one, but then I get some map phi 1, it might be a different map from what I actually wanted to get. And this is now where the invariant has to be enriched. So we need a different invariant to arrange that. We cannot always lift phi 0 and phi 1 simultaneously. We need a certain obstruction to vanish. So how about this obstruction? So first, you realize phi 0 as being induced by some correspondence. So this comes with certain unitaries UV and so on, and this induces, or this contains some UVs. And it induces some map on K1 that may well be different from the map phi 1 that we are given, we want to realize. Now we can change, however, our correspondence. We could replace the UVs by other unitaries. We have picked some unitaries to make this correspondence E, but we could well have picked other unitaries. And these will be something like, well, maybe I call them WV times UV, where WV is now a unitary in, let's say, PVV. Or I should have called it QV, that was my notation before. So this UV was supposed to be unitary from, well, the direct sum of the images of QS of E to the image of QV. It was unitary like this. And if you're given two such unitaries, well, one will be just obtained from the other by multiplying with the unitary on this image of QV. That's the freedom you have composed with an extra unitary here. And a unitary on this thing would just be unitary in this corner algebra in B. So I can actually change E star a bit, and this is the only change I can do. If I go back to my K-theory computations, I wanted to induce a certain map on this K1 group. And I have the freedom of picking unitaries for regular vertices, these WVs. This means I can pick a map on this group. And if you work out what happens, the map on K1 can be changed by a map that factors through this. More precisely, I should talk about diagrams. I have this K1 group for every ideal coming from a finite set of vertices. And then here I have a corresponding subset of VREC, which is the relevant one computing the K1 of this graph C-star algebra. And so I really have a map of diagrams. And now there's another important fact, namely this here is, well, these are free abelian groups. So this is actually even a free object in a suitable category of diagrams. So if I would now not just take one C-star algebra, but I would take the diagram of all these groups, then the groups here would be projective. And so this is the beginning of a projective resolution of this diagram. And I want a map on K1 which factors through this group. And if you know enough homological algebra, you will see that this is exactly how you compute the X2 group from this thing to that thing. So, where was I? So I'm looking now at the maps between K1 of this ideal to K1 of the ideal, which is coming from phi 0 applied to this. So X would be something in P of my graph C-star algebra. And this map represents 0 in an X2 for this K0 diagram into the K1 diagram. Well, maybe this is phi 0x. So these would be diagrams that are indexed by these special ideals generated by finite set of projections in a graph C-star algebra. This kind of X2 class wasn't a surprise for Rasmus and me, because in a previous paper we had classified graph C-star algebras with finitely many ideals using K0 and K1 diagrams plus a so-called obstruction class, which is also an X2 class like this. So what we have found is now that we need this obstruction class in this X2 group to vanish. This happens if and only if we can realize both phi 0 and phi 1 at the same time by a proper correspondence. And when we can do that, this argument I wrote above in blue can now be realized. So if I have these maps phi 0 and phi 1, and now I should add something, namely I know that the obstruction class vanishes. So assume this, this assumption means that the obstruction class in X2 vanishes. Then we do get these correspondences going back and forth. And then the rest of the argument can also be pushed through, and we find that the composites can be arranged to be homotopic to identity maps. Okay, maybe let's write this down as a theorem then. Okay, and then well, let's do it with star homomorphisms on stabilizations. So A tensor compacts goes to B tensor compacts. Back and forth, whose composites are homotopic to identity maps. And furthermore, we can arrange that the ideal structure is preserved. So more precisely, these star homomorphisms here will induce maps between ideals, and they are the isomorphisms of ideals that are induced by phi 0. So if you have this isomorphism phi 0 between these monoids, it follows that at least the gauge invariant ideals form isomorphic lattices for A and B, and so the maps back and forth which you get will induce that isomorphism on the ideal lattices. They will restrict to the ideals accordingly. And the homotopics will also be constant on these ideal lattices, so they are, well, you might say homotopics of diagrams when you look at all these ideals as forming a diagram. And one addition, which was actually somewhat technical and difficult to get, is that we even can preserve the ideal structure if there are non-gauge invariant ideals. So maybe this was the last result in the paper, was an extra step to arrange for the non-gauge invariant ideals also to be preserved. If a graph C-star algebra has ideals that are not gauge invariant, this means that they are circle components or subquotients, let's say. So, for instance, functions on the circle would be a graph algebra. It's kind of the Kunz algebra 01. And of course, this has not many gauge invariant ideals, most of them not gauge invariant. And but it's very kind of an elementary kind of C-star. We can just do computations by hand. And so we could do some by hand argument with the generator of function in the circle and choosing these unitaries in the constructions carefully. So everything we are doing is choosing unitaries and projections and so on to induce the right map. And if you have these circle components, you can arrange these unitaries in such a way that the map on the ideal lattice is also the same. That was kind of the last rather technical step to arrange for that to happen. Another important point is, of course, that you can realize these circle components by looking at the graph and how the graph has to look like for these things to be there. And so if both graphs have these circle components, then you have the unitaries you need to fix these maps to also preserve those ideals.
Do you have any assumptions about your graphs in this theorem, like row finite, or is it general?
Yes, row finite graphs is always assumed. However, there is this adding tails trick, which you can do first to replace your graph by a row finite one. The invariants I'm using are up to isomorphism or up to Morita equivalence even. And everything I'm doing is up to Morita equivalence. So it doesn't really bother me to restrict to row finite graphs because I could just first replace my graph by a row finite one and then work with that. So you could apply this to all graph C-star algebras. Okay, so
Wait, Ralph. Are you saying that if you have a non-row finite graph C-star algebra, then it is Morita equivalent to some row finite graph C-star algebra?
There's another graph so that they are Morita equivalent, yes. That's this adding tails technique by Tom Forde and somebody else. I could look it up which paper it was. So it's maybe a bit like the tablet C-star algebra is, well, how is this related?
Well, how about minimal initialization of compact operators, the Podley sphere? It's definitely not row finite. So it's Morita equivalent.
Yes, the obvious graph is not row finite. So the trick would be to add an infinite tail to the graph so that you have much more projections, and then you do get the right result. Maybe I just, so I know that this result exists, and I can even give you a reference.
Okay.
If I just search it in my paper files. So it's Mooley and Tom Forde from 2004, adding tails to C-star correspondences. And maybe I should put this onto a new page since there was a request for this fact. So fact, which is Mooley and Tom Forde, 2004, adding tails. And I think if you look for that, you shouldn't find too many papers. And it just says that any graph C-star algebra is, I think it's only Morita equivalent, not isomorphic, but I only cared about that result, so I'm not sure what the restrictions are, but it's certainly Morita equivalent. And to graph C-star algebra, even of a regular graph.
Okay, so not only row finite, but also no sources, no sinks.
Yes, you can really make it regular. So if it wasn't that our results work perfectly in the row finite case, I would have happily restricted to regular graphs. That's good enough for the actual applications. So that's a nice trick, which you certainly want to know. If you work a lot with graph C-star algebras. So if you really need it, then you can assume regular graph, row finite graph at no big cost. Of course, if you then do some computations, actually this adding tails, the tails are infinite. So you always produce graphs with infinitely many vertices that way. So if you would now take this result or classification of unital graph C-star algebras, this wouldn't help you. You have to do the general case, and you can't just add these tails in this way. It would leave the class that you want to, for which you are proving your result. But for my result, it doesn't matter. Okay, and I think my time is kind of only 1 minute.
Yeah.
So there is kind of one result I mentioned at the beginning, but now I didn't have time to talk about that so much. That was a purely infinite case. So I did talk about this kind of homotopy equivalence, which is ideal preserving. Maybe let's just say if you know this, and if you know that you are that you have strongly purely infinite C-star algebras, then you can just take a paper by Kirchberg about classification of non-simple purely infinite separable nuclear and so on C-star algebras, and it tells you that in this case they have to be isomorphic. And so that is that result is actually a bit easier because the result really says that an isomorphism can be lifted, and we can show directly that, so we don't need the inverse and all these tricks, we don't need the homotopy equivalence. It's enough to know that a certain map is an isomorphism on suitable K-theory diagrams to get its a KK equivalence, because you also have some UCT-like statements. So if you look into the paper, the statement for the pure infinite case doesn't follow from this theorem it's proven earlier, because we don't need these more subtle homotopy results to prove it. But I think that's all I want to say today. So thank you for your attention and your questions.
Thank you so much, Ralf. Okay, any questions?
There should be two, but you have to moderate things.
Yeah, Tomek.
I have a question. First, maybe a comment. On the level of K0, everything is almost painless, almost tautological, because you started from a definition of a graph system algebra in terms of Murray von Neumann equivalences between projections.
Yes.
My question is about K1 level. So K1 requires homotopy.
Yes.
But this homotopy, in classical algebraic topology, homotopy could be realized in terms of some paths, or sometimes in terms of some simplicial constructions. My strange feeling here is that maybe there is some more formal object than the sister algebra, taking into account some kind of homotopy in the sense of simplicial. Maybe it's a simplicial sister algebra. I don't know, whose structure uses all these things which are necessary to get your results, and by accident, when some vanishing of some obstructions, vanishing of some x allows you to truncate this full, let's say, simplicial object to something concentrated in degree 0, then you obtain your result for graph system algebras. Is it probable that something happens?
Well,
like this
I think you might want to get rid of this obstruction class in what you said, and that I don't think that's desirable, because for the graph system algebras, it's, well, K1 really is the kernel of this map between these three abelian groups. And that is really the reason why there is an obstruction class. So when you want to, when you change your unitaries in the construction, you have a map here, but you want the map on K1. So there is, you can't just produce a map on K1, you can only produce a map here, and so you get only maps that factor through this. And that's the reason for this obstruction class. And I think this is a feature that you want this. Also, the classification shouldn't be possible by using only the ideals and their K0 and K1 data. If you look into the result by Eilers and Restorff and Ruiz and others, maybe, I don't remember all the authors right now, then they are actually using a different invariant, which also takes into account subquotients. If you have an ideal, you can also take a quotient. It also has a K group, and you have an exact sequence there, and you have lots of exact sequences from all these subquotients. And the diagram formed by all this stuff is the invariant that they are using. Rasmus, Bentman, and I are only using the ideals and their K theory, not the subquotients. And that isn't enough information, really. But the obstruction class handles the extra information in a certain sense. This is also something we observed in previous classification results. So sometimes for graph C-star algebras with only a finite number of ideals, there are different classification results. One would use this filtrated K-theory invariant, and the other one would use well, the obstruction class and the diagram of K-groups for ideals only. And both are known to classify, so you should be able to go back and forth between them, but this is a very subtle thing. So, of course, there is something more formal, that's the Levitt path algebra. And you might wonder whether these ideals also apply to them. In that context, maybe you don't like homotopy so much, but that's kind of, well, let's say in my computation, homotopy mainly came in because I can't really, well, how unique are these unitaries? There's a lot of choice in these unitaries. They can easily multiply by any unitary, so there's a lot of freedom there. And homotopy was my best kind of guess how I could handle this huge freedom and make these unitaries at least unique up to something. Actually, it would be very nice to replace homotopy here by something like approximate unitary equivalence or something like that. Yeah. Then you would really then you could feed this into the intertwining argument and get an isomorphism. But we couldn't do that. Well, except in the purely infinite case where, citing Kirchberg, we actually know we can do it. But that's kind of the big hammer. We couldn't find an elementary reason why we could improve homotopy further to approximate unitary equivalence. Yeah, so Tomek seems to be frozen.
Oh, indeed.
I'm not sure who else is frozen. At least I'm not frozen. That's good.
Yeah, he seems to, yeah. Okay. And now what? He's still. Tomek, are you there?
I don't believe it. If he's frozen video, then
you are muted. You are muted.
Oh, sorry. So I lost a few sentences from
Ralf. Yes, you were frozen, so your connection was
frozen. Yes.
So let's say I'm not convinced how your idea of simplicial things might work and why it would be useful in that way. It would be useful to look at Levitt path algebras, and certainly homotopy wouldn't be the right thing there, but I couldn't do better than that, and so we left it at that. In fact, this paper got published only so recently because I wanted to get more and had some ideas that didn't work, and in the end I just decided this has to be finished, and I just finished what I had and put it out, and somebody else might then maybe continue and improve this further to replace homotopy by something else. But that seems to be difficult.
So maybe I should explain that I do not insist on using these simplicial methods. It was a placeholder for some formalizations of homotopies in such a way that they could be put into the presentation of a type of an algebra for which this classification would work without this vanishing of these abstractions.
Yeah, well, but here my comment was that I think the abstraction class should be there. It's a feature, not a bug. You want it to be there. Okay. So there's different classification results using more or less complicated invariants. And roughly speaking, when you want to classify, often you want to have a universal coefficient theorem. And that means that you have some kind of length 1 projective resolutions. And then you can classify very nicely using this invariant. Sometimes we have a simple kind of invariant where you don't have these length 1 projective resolutions, but you might at least have length 2 resolutions. And in that case, there is a classification using some abstraction class in Ext2. And there might be a different invariant, which is more complicated and has length 1 resolutions. And then you have two different classification results, but they both have their pluses and minuses. You could either use a more complicated primary invariant, or you could use a simpler invariant plus an abstraction class, which may or may not be simpler in your point of view. So in this infinite ideal lattice situation, homological algebra doesn't work so well. So actually, there is currently only this more elementary method, where the abstraction class just comes up by hand. So we don't use any sophisticated homological algebra to see it. So that's kind of nice about it if you really want to treat graph C-star algebras with infinitely many ideals.
Okay, thank you.
So Tomek, you are done, right?
Yes, I'm done. I'm very satisfied.
Anybody else? Adam?
I'm happy.
Okay. Cool. Okay, so let me wind it up. So first, I'm kind of in desperate need of some example illustrating your theorem. Can you provide one?
an example where this
Yeah.
isomorphism is really used.
Yeah.
Well, that's a good question. My work here was always rather theoretical. I didn't look at concrete examples. And of course, if you want to have an example where you go beyond the existing methods, you would need a graph C-style with infinitely many ideals. And then you would still have to know about this invariance. So I think any example would already get pretty complicated. So I would see this more as a theoretical result where examples, I suppose, would be contrived to be examples for this. So it was an attempt to push the classification further and, well, remove restrictions on the existing theories. Of course, if you look into the papers by Eilers and others about the unital case, they have all these moves, and this gives you also examples of root-equivalent graph C-star algebras. Now you would like to see examples where these techniques don't apply, but this one does. And in fact, I suppose Søren has given some talks about situations where he did use the classification result to prove isomorphisms, maybe where he couldn't see them immediately, I think, but I don't remember what these examples were. So examples in this business of classification are, well, not so common, I would say. Sorry for not giving you any examples.
No worries. I'm also wondering, it's very vague, but let me try to ask it anyway. There is, I just got an email from Søren about a result of Kirchberg and Phillips, or, two independently obtained results, in which they say that under some assumptions, I guess these have to be these things classified by Kirchberg and Phillips. So I guess these are simple C-star algebras. They have a result, as Søren explained to me, that if K-theory allows a morphism between these C-star algebras, then it actually exists.
Yes.
And how does this theorem relate to your theorem? Any common middle ground?
Yeah, that's in some sense how we prove this result. So the Kirchberg-Phillips classification theorem, well, has a strong version which tells you that every map on K-theory can be lifted. And that's in fact the first thing that we are proving. And then later on we look at isomorphism questions or homotopy equivalence questions. So the main technique here was to take a map on K0 and K1 like data. K0 was hidden as this monoid P of A, which is a diagram of K0 plus groups if you want. And then K1 was also a diagram, but if you think of simple C-star algebras, then of course there is no diagram. There's just one K0 group and one K1 group. Maybe it's a K0 plus group. And then my first step was realize the map on K0 plus by a correspondence, and then try to change the correspondence by fixing these unitaries in a different way so that the map on K1 is also the one that you want to reach. And this obstruction class was the obstruction to being able to do this. And so now we have obtained that this K0 and K1 diagrams together with the obstruction class would be the complete invariant up to isomorphism, at least no up to homotopy equivalence, let's say, or in the pure infinite case up to isomorphism by, well, getting maps both ways and arguing why they are inverse to each other up to homotopy, or at least KK equivalences, and therefore could be realized also by isomorphisms. And we also have results about correspondences from a graph C-star algebra to any C-star algebra. If you want, you could also get some kind of UCT-like statement. So you know UCT for KK theory, KK has a map to Hom, and then it has an X1 term. So here it's a bit different because there's an X2 term as well. And there's in fact like a spectral sequence. So there's a map from Hom to X2. This is the obstruction class map. And you only realize those maps on K0 and K1, which are on the kernel of this boundary map, this abstraction class map to X2. And then there is an X1, which gives you the, well, let's say the homotopy classes of those correspondences with the same map on K0 and K1. And then the X2 doesn't appear anymore except in the obstruction class map.
Mm-hmm. Okay, thank you. Since I see no further questions or comments, let's thank Ralf again. Let me stop recording.